Okay, let's look at this one. We have a three-phase synchronous generator. It's in a Y connection. Okay, this time is a bit different. So previous two example are all delta connection. This one we got a Y connection. And the single-phase equivalent circuit still look like this. And the reactance is 1.0. And we do not have neglect this resistance. And the full load is 60 amp, power factor 0.8 lagging. In this generator, we have this loss and this loss at full load. Things the armature resistance being ignored, then we assume this losses on the resistor also neglectable. The field current has been adjusted so that the terminal voltage is 480. Okay, so I think here is a bit of something confused. I think this voltage here corresponding in this circuit is this voltage. Okay, we can call this a phase voltage, no problem. And this voltage, I think, is the terminal voltage. Okay, also is the line to line voltage. Okay, in this case is 480 volts. But in the previous sections is all delta connections, so the phase voltage and the terminal voltage are exactly the same. But here I prefer to call this a phase voltage. And this is the terminal voltage. And you can see the conclusion, from the solution as well. But the solution was using VT here, so you know this VT is talking about this voltage. All right, so I will use the solution notation here, but you know that terminal voltage is actually here. Okay, is the voltage across the line voltage. Okay, so when the citation field current is fixed, then this EA is fixed. Okay, EA voltage is only related to that current, field current, and we know that at no load condition the terminal voltage is 480. So we want to convert the phase voltage equals to line to line divided by √3, or the magnitude. Okay, then we know that this is 480 divided by √3, and that is 277.13 volts. Okay, and we know this is 277, and because there's no load, so the EA, the internal voltage or armature voltage, is also 277. Okay, so that's the beginning. So what is the terminal voltage of this generator in the following case? Then EA will not change no matter what the load is. Then we're going to have 3 loading condition. It will definitely affecting the current, but the EA will be the same. We're going to see that. Okay, so start from here. We start to calculate the first question at the load 0.8 lagging power factor. Then what we do? So the current is going this way. The power is a flow from left to right. Okay, so this is a high voltage, and at the EA, high voltage, I think you can't see that. This is a high voltage, and drop, there's nothing. So high voltage drop equal to that. So this VT, okay, we're still using VT here. So this VT plus JXI IA equals to EA. Okay, with a angle delta. All right, so we write like that. So EA equal to VT. We usually give a reference for this terminal voltage or phase voltage here, 0 plus 190 degree, and that's the current. Okay, we did this several times. So the 60 is from here is 60 amp, and this negative 36 is from the power factor. Is arc cosine 0.8 is this amount. All right, we did this several times. And if you look at this one, you will find then we combine this two. Okay, 1 multiply 60, 90 plus negative 36, we got a 53.13. And up until here, it's really hard to solve because we got a two unknown. Okay, two unknown. We do not know delta. We do not know VT. Okay, we do not know the magnitude of the terminal of the phase voltage here. We do not know. So you can't solve it directly, but we can use some trick here. If we extend this is 0 degree, so it's only real parts. So that's the real parts. And 60, this phasor, we can convert it to a complex form, is 60 multiplied with cosine, this amount, and J 60 sine amount. Okay, so the phasor form E angle with the angle delta have a equals to A plus JB form. Okay, so E, the magnitude, gonna equals to A squared plus B squared. Okay, A squared plus B squared. So that was the cosine 53 degree. That was the sine 53 degree. Okay, then we know this E is how much is that? 277, right? This is 277. Then there's only one unknown VT. Then we can calculate that VT. It can be called a terminal, or I will rather call it a phase. And you can know the line-to-line voltage or the actual terminal voltage is multiplied by root 3 is 6.9 root 3, and that answer is 410. Okay, and you can see at no load condition the terminal voltage is 480. With load, the terminal voltage becomes 410, is reduced. Okay, that is actually not quite acceptable for grid-connected synchronous generator. So in real world, when you operate synchronous generator, there is a voltage control loop, which is constantly using a feedback to constantly control the excitation current to change the EA so you can maintain the VT. All right, somehow look like the first question we did. Okay, but this is just an example showing you if you have having load, the output will reduce to 410 from 480. And then if you have unit, okay, and you can draw the phasor diagram as well. So the VT is a reference at 0 degree. IA is a negative 36 degree and 60. And this one is perpendicular to this IA. And this one plus this one is EA. EA is a fixed number, okay? And then when the unit vector, this one becomes that little thing IA and X, because IA and VT are aligned. There's no phase difference. And if the IA is leading, then, the VT is larger than EA. Okay, you can see that as well. This VLL is 535, and this VLL is 468. All right. Okay, so that's pretty much the first question. Okay, you can do the math yourself here, just using this E squared equal to this thing. Okay. And the next part is what is the efficiency of the generator when operated at rated current. You can see this one. So the output here equal to 3 phase multiply with 236.9, and this is the phase voltage at here, right? We can actually using this phase voltage multiply with this phase current, which is 60, and multiply with the power factor, which is 0.8. Okay, and this is the I phase is equals to the I line. Okay, and if you remember that our universal equation is the root 3 VL IL power factor, that exactly match, because we can split this one with 2 root 3 and combine this one with a root 3 and convert this phase voltage to a line voltage, and that's the left. So you got exactly the same equation. Okay, so we said this one's universal, no matter it's delta connection, Y connection, you can always using this one. And the Pin, the input, that's the power sent to the load, and the power goes in, you need a plus to using this number plus two loads, two loss, 1.5 and 1. Okay, so 1.5 here and 1 here, then you got this in. And outputs divided by inputs, 100%, and that's your efficiency. Okay, and voltage regulation. The definition of the voltage regulation is, I think this is line-to-line voltage. This is also terminal voltage, in my opinion. Okay, and we should use this one to calculate the question 3. So the equation is you're using voltage at no load, okay, at minus full load. So this is the full load, and divided by full load. So no load is a full 180 minus full load, no load 480, full load of 410 divided by 410, and you got something here is 17.1. And if you do this one, and that is 2.6%, and the last one is yes, that one is 10.3. Negative, because you can see that the VT is even larger than EA. Okay, so the voltage regulation is a negative. It's negative 10.3. Okay, so this is actually the phase voltage regulation. Okay, so that is all about this question.